Hey Pete Calc, I did not mean to shut that video off. It just kind of happened when I closed out this screen. My bad. Before we move on to a new example though, number 8, I wanted to show you guys the actual graph to give us a sense for our final answer. So I went to Desmos and I graphed this, and it makes a whole lot of sense that we went from intervals of decreasing would be negative infinity to negative 2. 2, 4, 6, 8, 10, right? And then from negative 2 to 2, it's increasing. And then from positive 2 to infinity, it keeps decreasing. And then the inflection point is right here at 2, 4, 5. At 0, 5, we change from holding water up to pushing it down. All right. So it matches when we graph the function that increasing, decreasing concavity inflection points, they make sense. Let's go back now to some examples. So I'm going to do number 11 on the homework, on the problem set from which you got your homework examples. All right, so again, I'm going to ask you guys to kind of think your way through pre-calculus. What did a function like this look like? Well, if the leading power is even like this, and it's a positive leading coefficient, you know that the end behavior has to be this. Okay, it just has to. Now, what's going on in the middle is going to be determined by what else is happening in this function. So back in the pre-calc days, you kind of saw graphs that looked like that, or graphs that looked like this a little bit. So I don't know. My thoughts on the matter are it's probably going to look like this more than the other. I have not checked it out on Desmos yet, so we'll do that afterwards. Okay, part A. What are the intervals of increasing and decreasing? So the increasing and decreasing intervals. Well, hopefully we're pretty clear about the procedure. You take the derivative, which is 12x cubed minus 12x squared. Set it equal to 0. This is how we find our critical numbers. I can factor out an entire 12x squared with this. It would leave us with x minus 1. So you set this equal to 0, you get x equals 0. You set this equal to 0, you get x equal 1. So these are our two critical numbers by which we set up our intervals. All right? So we can go from, better do it over here, negative infinity to 0, 0 to 1, and then 1 to infinity. Plug in a half, plug in 2, plug in negative 1. Now we're plugging it into f prime of x equals 12x cubed minus 12x squared. It might be easier to plug it into the factored version. And you can do that. You can plug it into the factored version. The reason why I think it's easier is because when you take negative 1 and square it, it makes it positive. All right, so all I got to know is that when I plug in negative 1, it's a positive number times negative 1 minus 1, which would be a negative number. Positive times a negative is negative. So we're decreasing from negative infinity to 0. Seems to make sense. Now, if it's one of these dealios, this should be decreasing once again. What's 1/2 squared times 12? It's positive. What's 1/2 minus 1? It's negative. That's also negative, which means it continues to decrease. Ooh, that seems to be happening right here. And then we can be pretty sure that it's going to increase from 1 to infinity, because plugging in 2 yields a positive. So we can conclude that we are decreasing from negative infinity all the way to 1. Okay, you don't have to stop at 0 right here. Increasing over the interval 1 to infinity. There's part A. Part B is find the concavity. So now what I'm going to do is I'm going to take the unfactored version of the derivative, because that's going to be a way easier one to take the derivative of. Take the second derivative, you get 36x squared minus 24x. All right, and now these zeros are going to tell us potential inflection points. So 36x squared minus 24x, you can factor out a 12x. And that leaves you with 3x minus 2. So the zeros are going to be, again, 0. And this one will be 2/3. These are going to guide our intervals that we're testing now. So go from negative infinity to 0, make a pit stop, go from 0 to 2/3, make another pit stop, and then go from 2/3 to infinity. Test -1, test a half, test 1, into the second derivative. And you know what? I think I'm going to go with, I'm going to go again with the factored version of it. So you're testing by plugging in here, 12x times 3x minus 2. All right, plug in a negative. You get a negative number here. Plug in a negative, you get a negative number inside here. A negative times a negative is a positive. Makes sense. It seems like this part right here should be concave up. It's holding water up. Plug in a half. It yields a positive number there. 3 times a half is 1.5 minus 2. That's negative. Negative times a positive is negative. Makes sense. Right about here, it seems like it's pushing water down for a little while. So it's concave up there, concave down there, and when you plug in 1, it's going to be a positive times a positive. It goes back to concave up again. So we are concave up from negative infinity to 0 in union with 2/3 to infinity. And we are concave down from 0 to 2/3. And I can't remember. I know brackets are used for intervals of increasing and decreasing, but I think concavity might be parentheses instead. I need to look into that again. All right, last thing. What are the points of inflection? They're the places where you change from concave up to concave down. So 0 is a point of inflection, but so is 2/3, because changing from a concave down to concave up also satisfies the point of inflection definition. So we got this info, we've got that info, and then we've got inflection points. And I'll just give the x coordinates to save some time. At x equals 0 and x equals 2/3. Okay. You want to check Desmos and see if this is pretty accurate? I don't know if you guys can see that. Yep, they could be cousins. They've got definitely pronounced chin right there. Okay, next one. And it's the last one. These kind of take a while to unpack. Number 14, it's a trig one. F of x. I'm just going to assume it's f of x. If it's g of x, don't make a big deal about it. All right, and then we're stuck between 0 and pi. So this function kind of goes on forever. It's got cyclical behavior. They're just saying, hey, from 0 to pi is all we're looking for. So increasing and decreasing intervals. Take your first derivative. Remember, this square here is the same as a square out there. So you bring the 2 down, repeat the inside, then times the derivative of the inside. So chain rule is still in effect. It's going to be cosine of 2x. That's the derivative of sine, but then you still have to take the derivative of the inside. So the very most inside is 2x. Derivative of 2x is 2. So f prime of x is equal to 4 times the sine of 2x, cosine of 2x. Now, I'm not going to say I'm going to cheat here, but I do recognize something going on here. Remember your formula sheets from back in the day when we had trig identities? Yeah, this is a double angle formula. The double angle formula is, so we're just kind of, little thought bubble here. We're thinking, 2 sine of u cosine of u is equal to the sine of 2u. And all I got to do here is erase that. Say it's 2 times that, where the u is 2x. So it's going to be the sine of 2 times 2x. So you can replace this with the sine of 2 times 2x, sine of 4x. Now, there was an extra 2 out front, so it's going to be 2 sine of 4x. My apologies. If you weren't thinking we were going to use that formula, we are. So then 2 times sine of 4x, got it. You set it equal to 0. We have to remember how to solve trig equations. Remember, you can divide out any constants you want. This indicates that there's going to be 4 times as many solutions between 0 and 2 pi as you normally would. Sine equals 0 at 0 and pi. But it also equals at 2 pi and 3 pi and 4 pi and 5 pi. That's what it means to have 4 times the number of solutions between 0 and 2 pi. These would normally be your only solutions. This would be if it was the sine of 2x. This would be the sine of 3x, 3 times as many solutions. This would be 4 times as many solutions. And then what you do is you divide everybody by 4. So I just reviewed a bunch of trig right there. Hopefully you guys are okay with it. Bottom line is this. We're stuck between 0 and pi. So 0 doesn't work because it's less than 0. 0 is not included on that. So you can just get rid of the 0 right away. Pi over 4, you would include that. Two pi over 4, you'd include that. It's pi over 2. You know what? I'm going to start my intervals. Well, no. I'm not going to start my intervals just yet. 3 pi over 4 works. But then once you get to 4 pi over 4, that equals pi. And you need to be less than pi. So you're no good, you're no good, you're no good, you're no good. As Carly Simon said many times. Okay, these are our critical numbers. So you set up your intervals with those in mind. And the boundaries aren't going to be negative infinity to infinity. The boundaries are going to be 0 and pi. So you start at 0. You travel to pi over 4. Then you go from pi over 4 to pi over 2. Then you go from pi over 2 to 3 pi over 4. And then you go 3 pi over 4 to pi. I know, this one's just a pain to have to work through. Okay, so we've got that. So what are we plugging into? Well, I think plugging into f prime of x, this version of it, is probably our best bet. So this is going to be pi, oh boy, you know what? I'm just going to go right smack down the middle. Pi over 8 is exactly halfway between pi over 4 and 0. You guys can just go do radian decimals if you want to, and straight plug them into your calculator. That's probably an easier way of doing this. I tend to like to go the tougher routes. So this is like 2 pi over 8 and 4 pi over 8, so that's 3 pi over 8. 4 pi over 8 and 6 pi over 8. Plug in 5 pi over 8, and then this will be 7 pi over 8. Anyway, those are kind of the numbers that live exactly in between the two boundaries. And kind of the reason why I picked it was because I could see in the future that, hey, if you're taking 4 times each of these values, it's going to cross-cancel with the 8 and put a 2 on the bottom. So really, it's like I'm saying, what's the sign of pi over 2? 1. 1 times 2? Positive. You're increasing. This will be cut down to 2. Sine of 3 pi over 2? Negative 1. Negative 1 times 2? That's going to be decreasing. And then when it's 5 pi over 2, you recycle back and it has the same behavior as pi over 2. So this one's going to be plus, and this one recycles the behavior of 3 pi over 8. Okay, so you're increasing from 0 to pi over 4, and pi over 2 to 3 pi over 4. And you know what? I'm going to put a parenthesis around my 0 because it's not inclusive there. All right, so it's increasing here. It's going to be decreasing. I guess we're, yeah. Pi over 4 to pi over 2. And then 3 pi over 4 to pi. No bracket, parenthesis. No bracket, parenthesis. My apologies. Wow, okay. That was just the intervals of increasing and decreasing. How about the concavity? Well, luckily this simplifies things for us. The derivative of sine is cosine, so it's 2 times cosine of 4x. And then you take the derivative of 4x, which is 4. I'm just going to change this to an 8 now. There's our second derivative. So where are all the places that cosine of 4x equals 0? Well, I think I want to go off to the side here on this one. Right, we can divide out the 8 right away, so I'm not going to include it. Well, cosine equals 0 at pi over 2, at 3 pi over 2. These would be the normally 2 solutions. It seemed like in the previous example, we would have 4 times as many solutions right there. So 5 pi over 2, 7 pi over 2, and then 9 pi over 2, 11 pi over 2, and then 13 pi over 2, 15 pi over 2, and then you divide everybody by 4. Here's the thing, though. You're going to get pi over 8 right here, 3 pi over 8 there, 5 pi over 8 here, and 7 pi over 8 there. Everybody else is out of bounds. They're all going to be bigger than pi. So we can test those by starting at 0, going to pi over 8, pi over 8 to 3 pi over 4. Sorry, pi over 8, not. There's a lot going on here. Yikes. I'm glad I didn't assign this to you guys. That would have taken me a long time to do. Gotta keep focused here. Mercy. Come on now. We can do this. All right. Got them all? Wow. So I'll show you guys the alternate strategy. The alternate strategy is to say, okay, what is pi divided by 8? Clear all this off. Pi divided by 8 is the same as 0.39 radians. So if I put like 0.2 radians, that's fine. 3 pi over 8 is 1.178 radians, so I'm going to put 1.2 radians in there. I'm sorry. I am sorry. That would work there. It needs to be more than 3 pi over 8. Pi over 8 radians is 0.39, so maybe I'll put 0.4 in there. Although that's really close to 0.39. I'm going to go 0.5. This is 1.96, so I could just plug in 2 radians there, and then 7 pi divided by 8 is 2.7. Or just say, you know what, this is 3.14. Yeah. Plugging those into 8 cosine of 4x. Here's what it yields. So 8 cosine of 4 times 0.2. It's a positive. Concave up. 8 times the cosine of 4 times 0.5. That's negative. Concave down. 8 times the cosine of 4 times 1.2. Positive. Concave up. 8 times the cosine of 4 times 2. Negative. Concave down. So as you can see, guys, there should be a pretty solid pattern here. And this video is kind of extending long. We're already on almost 23 minutes, so I'm gonna kind of stop here and just say, these are your concave up intervals. Okay. And then these two would be your concave down. With inflection points at pi over 8, 3 pi over 8, 5 pi over 8, and 7 pi over 8. All right, guys. Hopefully this was enlightening, not more confusing. And I will post an extra credit problem set on Google Classroom. So, thank you for watching.